has been welcome to attend the Top Scientist webinar this morning while he is in the middle of his busy schedule at University Malaya. Good morning, Prof. Wan.
Yeah, morning. Very welcome.
Our Honorable Dean of Vocational Faculty, Professor Dr. Isfenti Sadalia, SAME. Good morning, Prof. Isfenti.
Morning.
Our Honorable Lecturer from the Vocational Faculty and the Faculty of Mathematics and Natural Science, Universitas Sumatera Utara, who attend the webinar this morning. Our Honorable ladies and gentlemen, who cannot be mentioned one by one, and also to our proud students who have attended this morning's webinar. First of all, let us express our gratitude to Allah Subhanahu wa Ta'ala for His blessing and mercy, especially the blessing of health and opportunity, so that we can attend the Top Scientist webinar this morning. In addition, we also express our salutation and greetings to our noble beloved, the Prophet Muhammad Sallallahu Alaihi Wasallam. Hopefully, we'll get his syafaat on the next final day. Amin ya Rabbal Alamin. Good morning, everyone. Thank you for joining us today. My name is Agung Pratama, and I am the lecturer of the Chemistry Diploma 3 study program, and also the moderator of today's webinar. This morning, Monday, July 22, year 2024, we will be together conducting a Top Scientist webinar activity with the topic Surface Enhanced Raman Scattering, or SERS, in biosensing. I am honored to be your host for this exciting webinar. Okay, the first agenda is opening speech from Dean of Vocational Faculty, from Professor Dr. Isfenti Sadalia. Time is yours, Prof. Isfenti.
Thank you, Mr. Agung. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone.
Good morning.
First of all, I would thank to God, Allah Subhanahu wa Ta'ala, who has been giving us blessing and mercy so we can join today's in good condition. Welcome to this webinar on surface enhanced Raman scattering SERS in biosensing, organized by the Diploma 3 Chemistry program at the Faculty of Vocational Studies, Universitas Sumatera Utara. As the Dean, I'm honored to host this event, which brings together experts and professionals to explore the exciting application of SERS technology in biosensing. The Diploma 3 Chemistry program is committed to providing our students with the latest knowledge and practical skills. This webinar aligns with our mission to bridge the gap between academia and industry, empowering our students to become leaders in biosensing. A special welcome is also extended to the guest speaker joining us today. We have the privilege of hearing from our keynote speaker, Professor Dr. Jefrey from the University Malaya, whose groundbreaking research has significantly advanced the field of SERS-based biosensing. We appreciate your willingness to share your knowledge and expertise, and I'm confident that everyone here will gain something from your presentation. In conclusion, this webinar will be a valuable and informative experience for all of us. So let's make the most of this opportunity and take away something new and exciting to share with our peers. I extend a warm welcome to all our participants and look forward to a stimulating and enriched session. Please join me in welcoming from Professor Dr. Jefrey Basirun. Thank you all for joining this webinar.
Assalamualaikum warahmatullah. Very much
Ah.
thank you to the Dean of Science, Professor Isventi, and also Mr. Agung for organizing this webinar. So my talk today morning is about surface enhanced Raman spectroscopy in biosensing. I have done Raman spectroscopy. I'm beginning to do Raman spectroscopy around 5 years ago, or more than 5 years ago. Originally, my PhD was in industrial electrochemistry, and then I branched into nanotechnology, material science, and now I've been doing Raman spectroscopy for the past more than 5 years. And I studied spectroscopy long time ago while I was in undergraduate student. And I find that spectroscopy is a very interesting subject because spectroscopy is very much tied to chemistry. And in the Department of Chemistry, we teach spectroscopy, many types of spectroscopy, vibrational spectroscopy, NMR, Raman spectroscopy, nuclear magnetic resonance, ultraviolet, and so on. And we teach our chemistry graduate in such that they understand spectroscopy more than any other graduate from physics department or medical faculty or engineering faculty. Because for chemistry students, spectroscopy is one of the core subjects. And because without spectroscopy, we cannot identify or solve molecular structures. That is why spectroscopy is very important. And for a chemistry graduate, whether Himalaya or any other university, you must explain or you must know what is spectroscopy more than any other graduates from different faculty or different department. So, and when I was an undergrad studying spectroscopy, I wanted to do my PhD in spectroscopy. But then I found out that at that time, there was very little application in industry. Because that time, around 30 years ago, the technical advancement of spectroscopy is still not very much compared to now, because now we have benchtop, everything benchtop, So, and then I explored to something very industrial, So, but now I find that spectroscopy has very much relevance to industry, to the biomedical field, especially when you're doing Raman, is very, very relevant to the biomedical field. In forensic science, spectroscopy used very much in forensic science, in analytical chemistry. Okay, so that is a power of spectroscopy nowadays, because you cannot actually separate spectroscopy from chemical sciences. It's a very much core subject in chemical science. Due to the advancement more than 30 years ago until now. So, like for example, if you are doing drug analysis, if you are doing a pharmaceutical analysis, if you are doing a biomedical detection of cancer, then you have to actually go into spectroscopy, as for example, Raman or any other type of spectroscopy. So the reason why we have actually ventured into Raman spectroscopy, because this is a Raman machine which is available in the university. In the university, we have 3 Raman spectroscope instrument, 2 in science faculty and 1 in the Institute of Nanotechnology. And this type of Raman, it costs very expensive, but there are advantages in researching into spectroscopy using this technique. We will see later. Okay. So this is the the outline of this presentation: bulk Raman, SCRS, plasmonic SCRS, substrate instrumentation, and application. Okay, so This type of spectroscopy can be used any type of sample, whether solid, liquid, even gases. If you have a container to store the gas, you can just put in the anechoic chamber and then get the spectrum. There's no sample preparation. There's unlike FTIR, you have kalium bromide or nujol. It is non-destructive, non-invasive. It can also work in situ and in vitro for biological samples. This is the one big advantage. And no vacuum. Okay, some spectroscopic technique need high vacuum. Okay, but Raman, you don't need vacuum. You can work under a wide range of condition, temperature, pressure. If you, for example, if your the chamber allows us to actually vary the temperature and pressure, then you can actually measure at different temperature pressure. Short time scale, meaning you put the sample, you get the result straight away. Can work with echo solution, glass wall, and these are the advantages. Okay, but in any spectroscopy, there are also some disadvantages. Disadvantages, like for example, pure metal alloy. This is very difficult. And also low sensitivity, especially for Raman. Raman is basic scattering technique. And also we have fluorescence for some material, then it's a problem. Fluorescence basically happen in mostly in organic compound. Okay, so these are the disadvantage. But however, when dealing with spectroscopy, basically there are, in terms of Raman, there are two types of what do you call vibration spectroscopy. One is infrared, and the other one is Raman. Okay, the difference between infrared and Raman, basically infrared you must have a dipole moment. Okay, for the molecule you must have a dipole moment. This dipole moment is due to the polarization of the molecule. Okay, like for example, the water molecule, most of the negative charge is on the oxygen, and most of the positive charge is on the hydrogen. So you have a dipole moment, meaning the electrons are shifted on the other side of the molecule, and the positive charges are shifted to the opposite side. So you have a dipole moment, but that molecule is still neutral. Like for example, hydrogen chloride is also it has a dipole moment. Ammonia has a dipole moment. Okay, so all these molecules has a dipole moment. Then that polarization is unchanging because the electron cannot be shifted to the opposite side of the hydrogen, and also the positive charge cannot be shifted to the negative side of the oxygen. It has what you call a permanent dipole moment. So this, when you have a permanent dipole moment, then that molecule, it can absorb radiation. We see, because spectroscopy is a study of absorption or the interaction of radiation, especially electromagnetic radiation, with the molecule or with the atom or with the ion. That is spectroscopy. Yeah? So spectroscopy studies the interaction of radiation, whether the radiation is what they call electromagnetic. That radiation must interact with the atom, molecule, or the ion. Then you get spectroscopy. So that interaction can, when that interaction happens, you have absorption. Okay, so when the water molecule or the hydrogen chloride or the ammonia has a permanent dipole moment, it absorbs the radiation, then you get excitation, and then you get relaxation. That excitation is a basis for the detection of the functional group or the bonding in infrared FTIR or infrared spectroscopy. Okay, so that permanent dipole leads to absorption of the infrared. Okay, and then that wavelength of the electromagnetic spectrum, which can interact with the dipole moment, it lies in the infrared region. That's why I call it infrared spectroscopy. Okay, there are some other radiation, like for example, we call radio waves, but radio waves interaction, you get rotation spectroscopy. Okay, but infrared interaction, you get IR spectroscopy. Yeah? So so that is infrared. Raman is basically a complementary to infrared vibration, because in infrared the molecule must possess dipole moment. In Raman, there is no absorption. Okay, there's only scattering. So meaning when you have the molecule, when the radiation touches the molecule scatters the radiation. It does not absorb. That is why we say Raman scattering and infrared is complement with each other. It is opposite because infrared involves absorption. When the radiation touches the molecule, you have absorption. Okay, but in Raman, when the radiation passes the molecule, it is scattered. It is kicked away. It is scattered in all directions. Okay, but so in Raman scattering, that molecule must not possess permanent dipole, because when the molecule possesses permanent dipole, then you get infrared absorption. Okay, so for any molecule or any function group in Raman scattering, it must possess what we call a phenomena called polarizability, meaning that molecule can be polarized. Okay, if that molecule can be polarized, meaning the electron can move in any direction, and the positive charge will be opposite direction. Like so, meaning that molecule or that group must be symmetry. Like for example, take hydrogen, oxygen, or nitrogen, N2H2O2. These are basically a symmetrical molecule. So when you have the molecule, when the molecules are symmetrical, there is no polarization of the charges on one side and opposite charge on the other side, meaning it can be polarized. So nitrogen, carbon dioxide is a linear molecule. Oxygen, hydrogen, chlorine gas are all symmetrical molecules. And this symmetrical molecule, there is no charge polarization, meaning the electrons are not on one side and the positive charges is not on the opposite side, meaning it can be polarized. The electron and the positive can be anywhere. Okay, so that is what we call polarizability. Okay, so when you have electromagnetic radiation, when it touches or when it interacts with the symmetrical molecule, then the molecule scatters the radiation because the molecule does not absorb. Okay, so the phenomena of absorption in Raman does not occur. In Raman, we only analyze the scattered radiation, because if the radiation is not absorbed, it is being scattered. That is how Raman works. So that's why Raman is complementary to infrared spectroscopy. So complementary in sense that the interaction of the radiation is opposite. So in infrared radiation interacts with the molecule or the group, then you have absorption. But in Raman, when the radiation touches or interacts with the molecule or the function group, there is no absorption, there is scattering. So this is why Raman is opposite to infrared radiation. We shall see later why infrared is not suitable for biological compound, because biological compound contains protein, amino acids, fats, and water, mostly water. And why Raman spectroscopy is suitable in aqueous or biological environment, because biological environment contains water and also protein and so on. Okay, so in this case, for a functional group or for a vibration for the function group, when it has in order to be active in Raman, you must have the change in a dipole moment must be zero. Okay, like for example, meaning that Raman vibration mode, there is no change in the dipole moment, meaning dipole moment is still zero. Okay, and like for example, when you look at a very symmetrical molecule, like for example acetylene is CH. So you in the carbon you have 3 triple bond. Between the carbon atoms you have 3 bonds, and then each of the carbon is single bonded with hydrogen. So it's a linear molecule, just like carbon dioxide, linear molecule. Okay, so when this molecule vibrate symmetrically, then it is Raman active. Okay, meaning symmetrically meaning the hydrogens move on one side, and the other hydrogen moves on the opposite side at the same length, so that the vibrational dipole moment is zero. The change in dipole moment is zero, because in order for the Raman, the molecule or the bonding or the functional group, in order to be Raman active, the dipole moment must be zero. There must not be any dipole moment, because if there is a dipole moment, then you get IR absorption. Okay, so in Raman, the most important thing that the dipole moment is maintained zero. So now we look at this vibration. So that molecule can be active both in Raman and infrared. Okay, does not mean that molecule, like for example, carbon dioxide, is a symmetrical molecule. Okay, the dipole moment is zero. It does not mean that carbon dioxide is only active in Raman and inactive in infrared. Okay, it depends on the vibration mode, not on the molecule itself. Like for example, look at this linear molecule. If this molecule, you have symmetrical vibration, meaning the hydrogen moves on one side and the opposite hydrogen moves on the other side at the same length, the dipole moment is still zero. When the dipole moment is still zero, meaning it will become Raman active, meaning that mode is Raman active. However, if the hydrogen on the right side move at a very long distance on the right, and if the hydrogen on the left side moves at a very short distance, meaning there is a dipole moment. And that dipole moment is due to asymmetric vibration, meaning the vibration is not symmetrical. You have the hydrogen on the right moving at a very far distance. The opposite hydrogen on the left moves at a very small distance, meaning now you have a dipole moment. When this mode, you have a dipole, when this vibration mode has a dipole moment, it is no longer Raman active, it will become infrared active. Like for example, when you have a linear molecule, so you have a symmetric vibration, it will be Raman active. However, when you have a asymmetrical vibration, meaning the vibration is not symmetry, then it will be IR active. Like for example, in this case, like for example, you can look at this example under below. When you have the both of the carbon, one moving up and one moving down in balance at the same distance, and the hydrogen, the one on the right is moving up and the one on the left is moving down at the same distance. So meaning this mode will be Raman active because the dipole moment is maintained as zero. Okay. However, when both of the carbon moves on top and both of the hydrogen moves below, now you have a polarized, dipole effect, meaning the electrons are not evenly distributed. So when this happens, that mode will be infrared active because it has a dipole moment. Okay, so that is the case. So whether the molecule can exhibit Raman or FDR, it does not depend on the symmetry of the molecule. It depends on the type of vibration, whether it's symmetrical vibration or asymmetric vibration. That will determine whether the molecule is IR active in the case of asymmetric vibration, or whether the molecule is Raman active in the case of symmetrical vibration. Right? So that is the case. So now, for example, in this case, you have a case of symmetric vibration. On the left is symmetric vibration, where the one carbon moves on top, the other carbon moves below, and then you have the one hydrogen moves on top, the opposite hydrogen moves below. So meaning this is a symmetric vibration. But however, on the right is asymmetric vibration because you have two carbon moving on top and two hydrogen moving below, meaning now you have a dipole moment. That dipole moment will allow this vibration mode to be IR active. Okay, so that is the determining factor whether the molecule exhibit Raman active or IR active. It depends on the vibration mode. It does not depend on symmetry. Also, like for example, you can look at the case of carbon dioxide. Carbon dioxide dipole moment is zero. but you have, so carbon dioxide is a linear molecule, just like acetylene. When carbon dioxide, when the oxygen moves at very long distance on the right, and the opposite oxygen moves at very short distance on the left, then you have a dipole moment. This type of asymmetric vibration in carbon dioxide will contribute to FTIR active or IR active. Okay, but when the carbon dioxide moves symmetrically, vibrates symmetrically, then it will be Raman active. Okay, so that is the determining factor, or why, or some meaning the symmetry of molecule does not determine whether it's IR active or Raman active. Only the vibration mode. For example, in a symmetric molecule, when you have what you call a symmetric vibration, then it will be Raman active. But when you have an asymmetric vibration, there'll be IR active. Okay, so now we look at this what you call complementary. So, like for example, these wave numbers in Raman and IR is basically collected from polystyrene. Polystyrene is a polymer which has a benzene ring and carbon double carbon. So you have the, you look at, so for example, you look at polystyrene, you have the carbon what do you call uh, uh, carbon bond, carbon single bond, and so carbon double bond in the benzene ring. Okay, so you can say that some of the Raman active vibration does not occur on the same wavelength or same wave number with the IR vibration. So this is basically why Raman and IR is complementary. So that is the case. Okay, so when we look at the scattering process, okay, because there are types of scattering. So like for example, you have the molecule, okay, and then you have the radiation, the wavelength. So when this wavelength radiation interacts with the molecule, you get absorption. Okay, if that molecule has dipole moment, you get absorption, and then you get FTR. But however, if the molecule is symmetrical, it does not have dipole moment, then you get, like for example, first of all, you get transmission. Transmission meaning the light passes through without being absorbed, without being scattered. And then you can also have scattering process. Okay, so when you have scattering, you can have elastic scattering, meaning when elastic meaning the energy of the incident light and the reflected light, they are the same. Okay, but most of it, the incident light and the reflected light, the energy are not the same. Okay, so when these energies are not the same, then sometimes the reflected light or the reflected radiation can have higher energy compared to the incident light. Or in some cases, the reflected light can have lower energy compared to the incident light. Okay, so I will not go into detail with the energy level, but this is the scattering process. So in when you have vibration, so meaning when the functional group or the molecule vibrate in a symmetrical manner, then this reflected light can have lower energy compared to the incident light, or in some case it can have high energy. Okay, so then you have what you call so this energy it is measured according to the wave number, because the reflected light the reflected light is measured according to the wave number. So that then you have the Raman, spectrum, Raman spectrum, the intensity with the wave number. So what we are measuring in this what do you call back to this thing, what we are measuring is basically the intensity with the wave number. That wave number is the reflected light, or the scattered light from the interaction of the incident light with the molecule or the functional group. So that you're measuring the reflected light. So there is no absorption measured, but there is only reflection. So when you look at the Raman spectrum, these wave numbers, we have the intensity, that is a reflection light or the scattered radiation, not the absorption. Because in Raman, there's no absorption, there's only scattering. Okay, so this is the process which simplifies the Raman process. Okay, so Raman spectroscopy provides fingerprint of molecular bond and crystalline structure in dependence on the environment condition. So like, for example, temperature, pressure, and because we know that temperature, pressure can actually influence the polarization of the molecule or the functional group. And so that's why it depends on the temperature and pressure. At the same time, in real life, what do you call, at the same time, this application of Raman is basically in real life, uh, it is hindered by a very low intensity, because what can we measure from scattering process is very low, because the intensity is very, very low. Okay, so that's why, for example, Raman spectroscopy was discovered in 1930s. Okay, but it took a very long time, for this technique to be available, because the scattering is very, very low intensity. So at those times, we do not have very good detectors which can very sensitive detectors which can actually detect the low intensity scattering radiation. That's why at those times, during the 30s or 40s, not much progress was being done on Raman technique, because the intensity of the scatter radius is very, very low, very, very low. That's why Raman spectroscopy was not very much advanced during that time. But however, when you have advancements of detection technique, when you have detectors which are able to detect a very low intensity, then Raman technique become very useful. Okay, so like for example, in the case of laser, so laser is basically, you have very a narrow wavelength. So this laser, when it very high intensity, when it interacts with the molecule or the functional group, it scatters the laser. So when this laser is scattered, you get a very larger intensity, which can be used to enhance this technique. So for example, when they use a laser, it has a source of excitation or the source of the incident light, then Raman spectroscopy became even more useful, because you can actually detect because the incident light becomes high intensity compared to the normal previous radiation without use of lasers. And also in the case of surface enhanced, and this method can actually enhance the sensitivity up to 10 power 14. So it is a very, very sensitive technique. Okay. And also microscope decrease the probe volume, meaning you can actually you can actually decrease the space you're actually analyzing. So that's why, so this becomes very, very sensitive. So this is a case of how Raman can be advanced by all these changes in technology. Okay, so the SIRS discovery was made during 1970s. Okay, when three people they observe when they absorb pyridine onto silver electrode, they observe the intensity become very, very high compared to just pyridine onto a non-silver electrode. Okay, so these guys are the first one who actually discovered this effect, and this was in Southampton University during 1974. It was reported in 1974. And like, for example, what is SIRS? Basically, SERS stands for Surface Enhanced Raman Scattering. Okay, so that surface is the key factor, the type of surface is the key factor for the enhancement of the scattered radiation. Okay, so that surface is a key factor, but this surface must, the molecule must be absorbed on the surface. So absorption, like for example, we have seen there can be chemisorption, when you have a bond between the metal surface and the molecule. When you have bond, then you have chemisorption, and also physisorption. Like for example, the absorption is based on charge interaction. If the metal is polarized, and the molecule is also polarized, it can be absorbed by charge interaction. So that will give us physisorption. So the key factor is that surface must be a special type of metal, and that metal surface must be able to bond with the molecule. Then only we can observe the SERS effect. So this SERS effect, why we name it enhanced because the signal is enhanced 10 power 14 times compared to just bulk Raman. That is the there's a advantage. So these enhancements, this enhancement can be divided in two types. One is chemical and the other is electromagnetic. We shall come to this later. So in this case, when you have a laser radiation onto the surface of the absorbed molecule onto the metal, then you have scattering. That scattered radiation is 10 power 14 times more powerful or more intense compared to just the normal Raman or the bulk Raman. Okay, so that is a case of the SERS. So the type of enhancement, we come this later. The type of enhancement can be divided into chemical enhancement and electromagnetic enhancement. Okay, so this is the same thing. So you can also do this in water. Like for example, in this case, this was the pyridine was absorbed onto the silver surface by just in air. So it just dropped pyridine onto silver surface, put in the Raman spectroscopy, you get the excitation. You can also do in water, in liquid. Like for example, when you have a pyridine molecule, where if you have a glass container and you have a silver electrode on top, and then when you drop pyridine, pyridine liquid, pyridine is a liquid in KCl, then you still can observe this effect, even though it is in a container which has water, I mean KCl water inside. So that is a case of the absorbed pyridine onto silver surface, silver metal surface. Okay, so what is different between SERS and Raman? SERS is a phenomena associated with the enhancement of the electromagnetic field surrounding small object optically excited near an intense and sharp plasmon resonance. So this has to do with plasmon resonance. So what is plasmon? Plasmon is a quasi wave which happens on the surface of the metal. Okay, and not all metal will actually give you plasmon resonance. We come to that later. Okay, and also SERS consists using a large local field enhancement that can exist on a metallic surface on the right condition. So only certain metal surface will actually give you plasmonic resonance. So when you have a plasmonic resonance, that will actually contribute to the what you call the electromagnetic enhancement. So like for example, first of all, this is the condition of SERS. You must have various certain metal, like for example, gold, silver, platinum. Okay, and the surface, metal surface must be rough on a nanometer scale, and the proper excitation laser wavelength. So this SERS will actually this SERS result, when we look at this SERS, the water, methanol, and most solvent does not give enhancement because they are not absorbed onto the metal surface. Okay, certain molecule provide much higher Raman intensity, mostly molecule with carbon double bond. Okay, so like for example, when the molecule is not absorbed onto the metal can be gold, silver, platinum, certain type of metal. When the molecule is absorbed onto the metal surface, this molecule or this bond function group absorbed on the metal surface, that will actually give you the Raman, the SERS spectrum. Okay, so when water is not absorbed on the surface, then water cannot give you the enhancement. Methanol, okay, all this solvent, water, methanol, it is Raman inactive because we have seen just now, water consists of dipole moment. Methanol is a polar molecule. It has dipole moment. So this water molecule, most polarized solvent, like for example, tetrafuran or water molecule, ethanol, will not give you Raman spectrum because it has a permanent dipole. Okay, only the function group when it absorbed onto the surface of the metal, and when the dipole moment is zero, it will give you Raman enhancement. Okay, and you have SERS when the molecule or the function group is absorbed onto a certain metal, like for example, gold, silver, or platinum, and so on. Okay? So that is a condition of SRS, SERS. Okay, so like for example, we look at this what we call example, like for example, rhodamine. Rhodamine is a organic molecule. So you look at the enhancement factor. One molecule of rhodamine will give you an enhancement of 7.3 10 power 9 compared to 7.8 times 10 power 5 molecules of rhodamine. So this is the enhancement factor. So one molecule can give you an enhancement factor almost 10 power 9. So one molecule in SERS, the intensity is more than uh, 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 around 100,000 molecule of the same molecule type of molecule without the what do you call the SERS. So this compares the SERS to the normal Raman or bulk Raman technique. Yeah? So that is the more what do you call I mean advantage of SERS compared to the normal Raman or the bulk Raman. Okay, so comparison, like for example, you have this molecule is sulfur hydrogen, a thiol group. Okay, so this thiol group, when it bonds to the gold surface, will give you a very high enhancement compared to just the normal Raman spectrum. So we can see this, the intensity of the SERS is around 16,000 compared to the intensity of the Raman is just only a few thousand. So this is the what do you call typical it has the molecule is not bonded to any metal surface, but in the SERS, that molecule or that function group must be bonded with the gold or the silver or the platinum surface. So that is the difference between Raman and the SERS, the normal Raman and the SERS. Okay, so this is a little bit of mathematics. I shall not touch on this equation. Okay, so so what are plasmon? So again, you see, plasmonic metal is a very important requirement for the surge phenomena, because without plasmon, the surge phenomena cannot be observed. Okay, so plasmons are quasi waves on the surface of metal due to the oscillation of free electron at the Fermi level. Because we see the metal, like for example, you have insulator. Insulator, when you have the conduction band, I mean the valence band and the conduction band for the insulator, the band gap is very high. Like for example, diamond. Diamond is the insulator. The valence band, conduction band is very high. For a semiconductor, it is intermediate. The valence band and the conduction band is around intermediate band gap. But for a metal, there is no band gap. In the metal, there's no band gap, meaning the conduction band and the valence band, the band gap is 0. And we name this as Fermi level. That is why metals, pure metal, like for example, all the metal in the periodic table, whether it's copper, nickel, gold, platinum, or iron, all of them have 0 band gap. This 0 band gap allows electron to move freely in opposite direction. And now, for example, when the electron can move freely, meaning it can conduct, that metal can conduct heat, because heat is a conduction of the electron knocking and what do you call colliding with each other. That's why metal surface or bulk metal is a very good conductor of heat. Okay, so that metal surface contains free electron, and that metal surface, when you apply a potential difference, then that metal surface will conduct electron. That is why metals are very good conductor for electricity and very good conductor for the heat, because metal consists of free electrons in the Fermi level. Like for example, diamond is a insulator because the band gap is very huge, and so diamond does not conduct heat, because the band gap is very huge. For semiconductor, the mangan is intermediate. So semiconductor can conduct what do you call electrons provided you have excitation. But for a metal surface, the band gap is zero. Zero meaning the electrons are in the Fermi level. Fermi level is the highest level where the electron resides or stays. Okay, so now when you have a metal where you have free electron in the Fermi level, this metal can vibrate, meaning this metal can oscillate. The electron can move on one side, the positive charge on the other side, and then it becomes opposite, and then it becomes on the initial arrangement. So you can have oscillation. When this electron oscillate, when this electron on the metal surface oscillate, then you get a plasmonic wave. That is how plasmonic wave happens, because the electrons on the Fermi level on the surface, when it moves on one side, the positive charges move on the other side, and when the electron moves to the opposite side, the positive charges move to the opposite side. So then you have what do you call a wavelength or a wave. So this wave is known as plasmonic waves. So, but not all metal can actually give you this effect. Like for example, if the metal is reactive, like for example sodium, when you expose sodium in air, you get sodium oxide. And when you have, for example, when you have aluminium, it absorbs what do you call magnesium. When it absorbs water moisture, become a film. So when you have oxide layer or film formation on the metal surface, then the electrons are fixed in position, meaning the electron cannot vibrate freely. That is why reactive metal surface, like for example, sodium, metal, magnesium, aluminium, ferrum, calcium, which can bond with oxygen in the air or water moisture, these metal cannot show plasmonic vibration or plasmonic wave. Only metals which have inert, metals are inert, like for example, gold. Gold is the best substrate to observe SERN and also to observe the plasmonic wave. Gold, all the electrons are on the Fermi level, and the gold surface is inert, meaning it does not bond with the oxygen in the air. It does not bond with the water moisture in the air. That's why you can also observe plasmonic wave on the gold surface, especially when these golds are in nanoparticle. Okay, and also like for example, silver surface. Silver is basically inert. As long as silver does not form a bond with the oxygen in the air or the water moisture in the air, then you can actually observe plasmonic wave. Okay, but to get a Raman spectrum of the molecule, that molecule must be absorbed onto the gold surface or the what you call aluminum or the what you call silver surface. Only that molecule, meaning that molecule can be absorbed, not the oxygen in the air, not with the water moisture in the air. Because if the water moisture and oxygen can be absorbed on the metal surface, then it becomes all what do you call it obscure the vibration of the analyte with the metal surface. So that metal surface must not absorb oxygen in the air. It must not absorb water moisture. It only must absorb the molecule which you want to analyze in the Raman spectrum. Okay, so and also this metal must have permanent dipole. Because when that metal has permanent dipole, meaning that metal vertical is active to FTIR, because we see the permanent dipole, whenever you have permanent dipole, then they become IR active. Okay, so or in other case, the what do you call because when you have a permanent dipole, becomes a dielectric. So for those who deal with work with supercapacitor or capacitor, you must have a material which has a permanent dipole, because this dipole can be flipped. It can change direction according to the electric field. So all these point, when you have a very large metal full of electron, and this metal does not form what they call bonding with the oxygen in the air or the water moisture in the air, then this metal can be polarized. then when this when this metal, the electrons are free to move. So when you have a metal which can be polarized into opposite direction, then you have the plasmonic wave. So like for example, metals such as gold, silver, platinum, these are very large metal, large atom full of electron, and they are inert compared to the inert, meaning they don't form bond with the water, moisture, or in the oxygen. So that's why they can actually give you the plasmonic effect. So this metal, like for example, gold, or for example, platinum or silver, these metals are perfect to show plasmonic because they don't interact with the oxygen or the water moisture in the air. Okay, so this is a plasmonic wave. So like for example, you see that in the electron in the metal surface, it's sometimes it goes on bottom and sometimes it goes on top. So when you have this type of vibration, you get a plasmonic wave. Okay, so like for example again, and surface plasmon resonance is where you have, because that this wave is, you have a certain frequency, and then when you have this wave vibrating a certain frequency, then when you actually interact with another frequency, external frequency, then you get a resonance. That's why you call it surface plasmon resonance. So plasmon is a quasi wave from oscillation of electrons on the metal surface. When irradiated with electromagnetic radiation, a super wavelength, the plasmon will resonate and produce a phenomenon called surface plasmon resonance, or SPR. So this SPR only happens on metal, like for example, gold is the best. Silver, platinum, and other metals which are inert to water, moisture, and oxygen content in the air. Okay. So like for example, again, so now we go into type of enhancement. We have two types of enhancement. One is electromagnetic enhancement, and the other is chemical enhancement. Okay, this type of enhancement happens at different levels, or different what do you call proportion. Okay, so chemical enhancement. When the molecule, because in SERS, the molecule must be bound onto the gold or the silver surface. So when the molecule is bounded to the plasmonic metal by chemisorption or p-sorption, when the irradiation of the laser radiation happens on the surface of the molecule on the metal, then you get a charge transfer. This charge transfer is from the metal surface to the molecule. Okay, so the chemical enhancement is due to the charge transfer from the metal surface to the molecule. So when you actually shine the laser to the molecule, and the electrons of the molecule become agitated, or it moves on opposite side, then you promote charge transfer from the metal to the molecule. Then you get the charge transfer effect, and this charge transfer will contribute to the chemical enhancement in the SERS. So chemical enhancement due to charge transfer from the metal surface to the molecule. Okay, so like for example again, when you irradiate the electron, sorry, not electron, I mean irradiate the laser onto the molecule, and this effect will actually alter the electron density of the molecule. This will actually result in greater polarization, so that polarization will actually enhance the charge transfer from the metal to the molecule. Then you get a what you call an enhanced Raman scattering. Okay, so that is basically around 10 power 2 to 10 power 4. So that is known as chemical enhancement. Chemical enhancement, the most important effect, there must be charge transfer from the metal to the molecule. And when this can only occur when the molecule is very close to the, or bonded to the metal surface. That's why only then you can observe charge transfer or the chemical enhancement. The next is electromagnetic enhancement. So now the chemical enhancement is a short range enhancement. Okay, short range. The second type of enhancement is electromagnetic enhancement. So electromagnetic enhancement, it happens due to the irradiation of the laser onto the substrate, and then that what you call promotes plasmonic resonance, and this plasmonic resonance will actually irradiate a secondary radiation, or scatters a second radiation. So that radiation is what you call is detected by the Raman detector. So this is known as electromagnetic enhancement. This electromagnetic enhancement is a long range enhancement. Okay, while chemical enhancement is a short range enhancement. So, like for example, in electromagnetic, only occurs in metal with surface plasmonic resonance. The external magnetic radiation can interact. The external electromagnetic radiation can induce the plasmonic resonance of the substrate. The plasmonic wave enhances the electric field around the molecule. The electric field in the molecule causes greater polarizability of, hence greater secondary effect of the molecule. So you have an enhanced signal. Okay. So the plasmonic wave from the interaction of the laser radiation with the plasmonic wave, it causes the electric field around the molecule to change. So in the electric field, the molecule changes, it causes greater polarization of the molecule. So when you have bigger polarization, you get enhanced signal. That is how the electromagnetic enhancement works. Okay? So when the Raman, but again, like for example, there's another secondary effect. When the Raman scattered light overlaps the plasmonic resonance, because this plasmonic resonance is in the metal, while the Raman's scattered is the Raman's light, which is scattered by the laser light. So when the laser light produces the scattered radiation, when this scattered radiation interacts with the plasma resonance on the metal, then you get another signal. Like for example, look at the left side, the one on the which is the one on the ungu, meaning the arrow which is dark blue. This is the re-emitted Raman scattering. So you have double effect. So this effect will actually give you the electromagnetic enhancement. This electromagnetic enhancement can enhance the signal unto 10 power 10 compared to a normal Raman or the bulk Raman. So this is a case of the thing. So this is the case of the SERS, where you have the metal surface, you have plasmonic resonance. The top one is a plasmonic resonance, and when the laser interacts with the molecule, then you get a scattering effect. This scattering effect can be due to chemical enhancement and also electromagnetic enhancement. Yeah? So this type of enhancement, okay, this local electromagnetic field near the plasma provides very high enhancement for the Raman scattering. So this SERS effect depends on the metal molecule affinity and the resonance condition, and the highest electromagnetic factor is reached at random hotspot. So, like for example, once you have this what you call this effect, this nitrogen or the pyridine molecule which is bonded with the metal surface, this is the hotspot. This hotspot contains very large enhancement. So, I mean, due to the electromagnetic. So that's why this we call hotspot. So the region between the nitrogen or the pyridine molecule and the gold surface, this is a hotspot. And this hotspot is very critical in Raman measurement of the or Raman detection of the molecule itself. Okay, so this is the best explained effect of the electromagnetic enhancement. Okay, so the search substrate, the substrate can be any metallic structure that produces SRS, as long it is a metal, like for example gold, silver, platinum. It must have metal surface with plasmonic wave, meaning that electron will not interact with the oxygen in the atmosphere or the moisture in the atmosphere. It is a free electron which oscillates on the surface of the molecule. So then you have the plasmonic resonance. And this plasmonic resonance is very critical for the electromagnetic enhancement in the Raman SERS. So, like for example, the substrate can be nanoparticle solution, planar metallic structures, and metal electrochemistry. As long you have the plasmonic wave on that metal surface. Okay, so like for example, you can also, this is sample preparation, mainly gold, silver, or copper nanoparticle in water. So in some cases, You can also have nanoparticle in solution. If you have a vial and this contains gold nanoparticle in solution, then you can also observe the SCRS of the gold bonded with the molecule. Okay, so example, this is the silver nanoparticle bonded with citrate. So you have the also silver gold nanoparticle bonded with sodium borohydride. These are all basically example of the SCRS effect. Okay, and also gold nanoshell or gold nanoparticle with the organic compound. Okay, we observe this spectrum. Okay, and a nanoshell, like for example, a silver and gold silver core shell structure in nanoparticle. So as long this gold surface bond with the analyte, then you can observe the SCRS effect. And also like methylene blue absorb onto gold nanostructures. So these are all typical preparation sample preparation sample of a gold and organic compound. As long the gold bonds with the function group of the organic compound, then you can observe this SCRS effect. Okay, so that is a summary. So summary basically, metal nanostructures provide huge electromagnetic enhancement for Raman scattering, making possible single molecule. So meaning when you have SCRS, when you have the metal surface bonded with even a single molecule, that will actually make detection possible because the enhancement is very, very huge, at 10 power 14. So this enhancement happens due to SPR, surface plasma resonance, which actually combined with the laser and the radiation to get a very high signal enhancement from the SRS effect. So sensitivity of AS can bursted and SRS fabrication distribution still may okay. For example, fabrication, distribution, and reproducibility still remain problem in SRS. So this is a what you call some drawbacks. Okay, so now we look at the can be used. So like for example, in this case, you have the Raman photon. When this molecule is absorbed onto the molecule, when this molecule is on the gold structure, then you measure the scattered radiation. So that scattered radiation it measured not on the same direction of the incident photon. So the incident laser it passes the molecule on one direction. The detection is on the opposite direction. I mean, not on the same plane has the incident photon. So that is a case of the detection strategy. Okay. So drawbacks, for example, the target analyte must have bonding with the absorption towards gold or the metal surface. One main drawback is fluorescence. Okay. Fluorescence is where the laser photons, if we absorb the sample at longer wavelength, low frequency, then the emitted signals are emitted. So meaning fluorescence is an absorption effect. Mostly happens in organic compound. So fluorescence is where you have the laser radiation absorbed by the molecule, and the molecule excites, and then it relax by releasing lower frequency. So this absorption is basically obscures the Raman signal. Okay, so one solution is to actually select the most suitable laser wavelength which does not produce fluorescence. Like for example, before starting a Raman experiment, we used to actually run the fluorescence first. For example, when you have pyridine molecule, run the fluorescence spectroscopy, get the result, and make sure that the excitation laser wavelength is not on the same wavelength as the fluorescent peak in the fluorescence spectrum. That is one what you call strategy. So that's why in a typical Raman spectrometer, you have at least 3 different laser excitation wavelength: high frequency, low frequency, and mid frequency. So you can actually choose which of these suitable for the compound, and suitable meaning it must actually able to differentiate between fluorescence and the normal Raman scattered signal. Okay, but usually for dealing with organic compound, you run the fluorescence spectrum. Make sure that the Raman laser excitation, it is not in the same frequency region as the fluorescence spectrum of that same compound. So that is a simple experiment setup to actually to solve the fluorescence problem. For example, so Raman spectroscopy, now we have handheld Raman, not the big machine, but just handheld, battery operated. There's no there's no need to plug in the main source, just battery operated, and this simple Raman technique can detect even very small amount of analyte. So Raman is basically like a fingerprint, because like for example in FTIR, like for example you compare the FTIR, the OH vibration, the OH of the water, of the alcohol, or of the acetic acid, or of the any molecule we have OH, it only occurs on between 3000 and 3500 wave number. But the OH in Raman spectrum, the OH of the ethanol, the OH of the water, and the OH of the methanol, it doesn't occur at the same region. That's why Raman is a fingerprint, because the same vibration, the function group in the same function group of different molecule will not occur in the same wave number in the Raman spectrum. That is why Raman is a fingerprint molecule. We shall see this later. But in FTIR, the OH of the ethanol, the OH group of the methanol, the OH group of any alcohol, of any water molecule, it always occur between 3000 and 3500. But in Raman spectroscopy, it's not the case. Okay, so we see some example. So now Raman, the hand is really used in all this industry, dye to detect illicit drugs, pharmaceutical, toxin, bacteria, and also pesticide, antibiotic, and so on. So, like for example, in the case of this is a report. To differentiate between methanol and ethanol. So, ethanol is basically you have OH group and also methanol. So you cannot use FTIR to differentiate between methanol and ethanol by looking at the wave region between 3000 and 3500, because the OH or the methanol and ethanol, it occurs the same region. But in Raman, it occurs a different region. Okay, like for example here, this is a Raman spectrum of methanol in ethanol. Okay, like for example, in the spectrum below is a case of the peak at 1035 indicate the presence of methanol 1035, and others, and this 1035 is only for methanol, not for ethanol. This is why Raman is a fingerprint a detection strategy to differentiate between molecules which have the same type of function group. Like for example, OH, alcohol. You can differentiate different alcohol using Raman spectroscopy, not by FTIR, because in FTIR all the OH vibration happens at between 3000 and 3500. But when you go to Raman spectroscopy, the OH of the methanol is not the same region as the OH in the ethanol. That's why this is a fingerprint detection technique. Okay, and another, for example, in terms of what do you call no, sorry, this one. Okay. Okay, so this is the case of a thing. Okay, so this is Raman processing. So this is a simple processing technique. You just put drop on the gold surface and then run the spectrum, and then you get the result. And also, like for example, in the case of nowadays they have portable Raman, which runs on battery power, not on a plug-in point. So you can actually detect explosive. Okay, as long that explosives are in the air, okay, in the air, and like for example, when you have a trinitrotoluene or dinitrotoluene, they can actually detect when you have the gold surface, and as long these explosives are volatile in the air, when the molecule absorb, when this molecule absorb on the gold surface, then when you run when you study in laser, then you get the spectrum. So this can be used to detect explosive and also drugs, as long the drugs and the explosives are volatile in the air. So that is the case. That's why they use this technique in airports, airports or custom to detect potential explosive, whether the person is carrying explosive, and when the explosive exposed in the air, it permeates in the air. Then when this molecule absorb on the gold surface, you give a Raman spectrum. And when this Raman spectrum is evident, then you get that this is a base of detection. Also for example, drugs, like for example, danger drug, like for example, methyl amphetamine, or heroin, or other danger drugs. As long it is volatile in the air, when you expose this Raman, what you call portable instrument on the air, when it touches on the gold surface, you get spectrum, and that spectrum can be based on this. So this is how they use Raman spectroscopy in airports, or to detect explosive, or to detect any what you call drug trafficking. So this is the case of a thing. And like for example, this is TNT. This is very explosive used in Raman. So this is the portable Raman. Okay. So this instrument is marketed by Metro Malaysia. Metro Malaysia is a local company. It markets portable Raman from Switzerland, because this what you call instrument is made in Switzerland. So this instrument, you have the electrode surface with gold. When you expose it, of course, first of all, you must do calibration of the what you call molecule onto that onto the instrument. So when this instrument is calibrated to detect explosive, and then when you expose this instrument, the gold surface on the contaminated air with explosive, then you get detection. So that is a case of this Raman portable SARS instrument marketed by Metro Raman. And then it's also good technique in biomedical, because in biomedical, for example, biological environment, you have water, you have protein, amino acids, fats. All this what they call molecule has this function group CO, NH2, and NH. So this will not be good in FTIR, because FTIR have very strong vibration of NH, NH2, OH between 3000 and 3500. Okay, so but these function groups are not Raman active. Therefore, Raman or SARS can be used in biological environment, because in biological environment, you have protein, water, mostly water, protein, and all this you have NH group, OH group, NH2. So all these are not Raman active. So they can be used to differentiate a molecule you want to analyze without the disturbance from water or protein, which consists of OH, NH, and so on. Okay. And like for example, these are the case of different thing. You can actually look at this. I mean, so in all of them you have the goal. You can use DNA sensing, can also be used in Raman spectroscopy. These are basically various type of results. Okay. And like for example, dengue DNA virus. Okay, using but these are all basically DNA. Electrochemical DNA sensing. So this technique can be also quantitative. Okay, quantitative meaning you have a what you call you have a certain concentration. You measure the concentration, and then you get intensity. And then when you go for an unknown sample, we can actually detect the unknown sample provided you have this calibration graph. So this is a quantitative technique. So, and this again, this is another result, and so on. So this is the calibration graph. So what do you call DNA detection? DNA detection can also be used in Raman SARS technique. So DNA detection, like for example, you can actually now differentiate DNA of because last time we have the horse meat scandal in Europe. So the dead horses, instead of throwing it away, they cut out the meat and then mix with what do you call cow meat or lamb meat, because to save the cost of the lamb and cow meat. So this type of SARS can be used for target DNA detection. And this is all the what do you call things about SARS. So those are the advantage of SARS compared to bulk Raman. Basically, the technique is simple. Of course, you have problems, but whenever you have a portable battery operated Raman spectrophotometer, we can detect contaminated air, then it become a very, very useful technique compared to the bulk Raman. The bulk Raman, you have a very big machine, you must plug in, so it is not very feasible. So that concludes my talk. So thank you very much. We can go to question and answer session. Thank you very much.
Okay, thank you very much, Prof. Wan Jefrey Basirun, for your interesting presentation and informative presentation. Now it is time for us to open the question and answer session. So we encourage you, all participants, to ask a question, share your thought in the chat, and actively participate in the discussion. Okay, participants who want to ask a question are pleased to state their identity first. Questions should be brief, concise, and clear. Okay, let's start the discussion session. I invite all participants to ask a question. Okay, maybe let's see in column chat. Yes, Prof. There is a question from Professor Rickson Siburian. The question is, could you express how to probe graphene by using Raman? Okay, this is the question from
Probographene.
Rickson Siburian.
Yeah, what is probographene actually? Is graphene, right? Probographene is graphene, right?
Graphene, yes,
Yeah,
Prof.
okay.
Could you express how to probe graphene by using Raman?
Oh, to probe graphene. Okay. Yeah.
Yes.
So meaning, yeah. Graphene and carbon materials are very much used in Raman because you have the ID and IG curve, ID peak, I mean ID and IG peak. So that peak, like for example, so for graphite is very, very much ordered, right? So the ID over IG. Okay, D stands for disorder. Okay, and IG stands for order. So those two peaks. If you refer to the Raman of graphite or graphene or carbon nanomaterial, any carbon nanomaterial, you have this ratio. Okay, so for graphite, the ID over IG is very small because the disorder in graphite is very, very small. Because the ratio depends on the disorder, no? Because it's a disorder index. Okay, so when you have D stands for disorder, and IG. Okay, so when the ID over IG is very huge, meaning the disorder is very huge. Okay, like for example, pure graphite, you have very low index of ID over IG because pure graphite is very ordered. Okay, because this ratio ID over IG, it measures the disorder ratio. It is a disorder ratio. Okay, so like graphite is very ordered. You have, all the graphite layers are ordered in perfect, what do you call, arrangement. So the ID over IG ratio is very, very small. Okay, compared to graphene oxide. Okay, graphene oxide is a single layer of graphene, but it has carboxylic group, it has carbonyl group, it has carbon OH group, it has many functional group, because when you oxidize graphite, you get graphene oxide. So this graphene oxide, the surface of the graphene layer is covered by carboxylic group. Some of it is carboxylic, some of it is a carbonyl group, some of it is a carbon oxygen OH. So that surface now become disordered. So now when you run the Raman spectrum, the ID over IG will be very much larger compared to pure graphite. That is how you measure the what you call that is how you analyze graphene material in Raman spectrum. But you have a perfect graphene layer absorbed onto a metal surface. Okay, now you can actually look at the defects, because if this graphene, because this graphene is perfect, no defects, no bonding with external molecule or atoms. If this graphene is perfect, then the ID over IG is very small ratio. But however, if this graphene has holes, because there is one criteria to differentiate whether the graphene has holes in it. I mean, they call it holy graphene, meaning graphene which have holes. So when this graphene is more, although this graphene is a planar 2D material, but if it has defects, surface defect, like for example, holes here and there, and bonding is broken, then the ID will become very large. The ID-IG ratio will become very large. But when you have a pure perfect graphene without defects, without external bonding with other molecules, then the ID over IG ratio become very small. That is one criteria that they use. This Raman, what they call spectrum of the graphene. This is one criteria they use whether to determine whether the graphene is a perfect graphene or graphene with defects. Like for example, you take a perfect graphene, graphene from graphite. Graphite is basically graphene layers. Now you, for example, when you oxidize graphite into graphene oxide, right? And then you run the IR, I mean the Raman spectrum, you get a very huge ID or IG ratio. Then you take this graphene oxide, reduce back to graphene using a very strong reducing agent. Then you should get a what you call a graphene layer. But this graphene layer is broken, meaning it's no more perfect. Meaning you have defects, you have what you call holes, because when the carboxyl group is being reduced, or when you expel a carboxyl group, you expel the carbonyl group, you expel all oxygen, then you get imperfect surface. When this graphene is imperfect, meaning you have defects, you have holes, then the ID-IG ratio will rise compared to pure graphene. That is how they use this technique, Raman technique, to determine whether the graphene is perfect graphene without defects, without broken bonding, compared to graphene full of defects, full of broken bonding here and there. That is how they use Raman spectroscopy, by looking at the ID and IG ratio. Hope that answered the question. Okay.
Thank you, Prof.
Okay.
Thank you so much, Prof.
What's the next
Okay,
question?
is it clear, Professor? Or
Yes,
any
thank you,
question?
Pak Agung. Yeah, very clear. Thank you, Prof.
Okay. Next question from Miss
Okay.
Marina. She has a question about sensitivity of SERS. If there is a sample contamination, could you please advise on how to address or mitigate the issue of contamination in SERS measurement?
Okay. Sample contamination, like for example, when you run the SERS, like for example, you are looking, okay. First of all, you must know what what is your target analyte. Like for example, if you use this machine or this small hand, like a size of a handphone, to detect, for example, trinitrotoluene, TNT. Trinitrotoluene. So TNT is basically okay, TNT is is the molecule on top here. You have CH3, and this is actually a explosive, but it is volatile. So when you actually run the Raman spectrum, okay, of this molecule, you must get the full spectrum, okay, and you want to differentiate between this molecule here and, for example, this molecule. I mean the 2,4-dinitrotoluene. There's no what you call the sixth position is absent. So again, because Raman is basically a fingerprint technique, okay, so the bonding between the gold metal with the molecule, and that will actually determine that will actually determine the whole Raman spectrum. Just like, for example, we have seen, like, for example, just now the what do you call we have seen, like, for example, just now the methanol and the ethanol, okay, that methanol ethanol. So now, for example, we want to detect methanol, like, for example, we run the whole Raman spectrum, okay, and if that ethanol is contaminated with ethanol, okay, then you will have a different Raman spectrum, right? Because when you combine, like, for example, here, this is the method to differentiate methanol from ethanol, okay? So methanol has this vibrational. You have around 1035. All this 1035 is due to methanol. Or, like, for example, the vibration around 1000 is due to ethanol. Okay, so you identify the molecule you want to run, you want to analyze. So you get the Raman spectrum or get FTR. Okay. Now, when you have contamination, okay, when you run the Raman spectrum again, you have the overlap of the spectrum of that molecule you want to detect with the contaminant molecule. Okay, like, for example, now if I have, for example, both ethanol and methanol in the same sample, whereas I only want to detect ethanol, right? So if I want to detect ethanol, I should get this spectrum, right? This wavelength here, and this wave number here, okay? And if I want to detect methanol, I should get this double peak here, okay? But if I run the spectrum where you have which I have both ethanol and methanol, therefore this spectrum will be overlap. When you have overlap, then you have all these peaks. This peak here, this one here, this one here, this one here. So, but this one is very evident because in ethanol, this does not occur, but in methanol, this occurs. So therefore, when if I want to detect methanol, but I have this peak here in the same sample, meaning this peak here is for the ethanol. So the best thing to run the full spectrum of the analyte you want to detect and run the spectrum of the potential contaminant of that analyte. Like, for example, I run the methanol spectrum. I want to get methanol. I run the methanol spectrum. I get this spectrum. But if there is ethanol, then I run the ethanol spectrum. I get the spectrum. But if there is a contamination of ethanol inside methanol, then these two peaks should be overlapped. When it overlaps, then when I detect this, I know that I have a ethanol contamination in that sample. This is one way to actually analyze. Okay. Another way is to what do you call? Not to depend solely on Raman. Basically, you can do other techniques, like, for example, UV, ultraviolet, okay, detection, because those can also differentiate between Raman and methanol, because the energy band gap is quite different. And what they call, like, for example, if you have, like, for example, methanol and ethanol, and you run the UV, you get different excitation, you give it different peak. But again, UV is basically is a bulk technique. You must have it is not the technique we can detect very small amount of sample. So like for example, in addressing contaminant, try not to stick on this technique, try to get other techniques, like for example UV or FTIR and other techniques. So I mean, like for example, if you have a, like for example GCMS, but all these techniques are basically bulk techniques. Gas chromatography, it can differentiate between ethanol and methanol, but this is a very big technique. It's a very expensive equipment. So when you get GCMS, you still can differentiate between methanol and ethanol. But we are talking about portable techniques. Like for example, techniques we can actually you can bring on site, okay, and detect that contaminant or that presence of the analyte at that site itself, not to take into the lab and run the sample. So you can also use GCMS. Like for example, if you suspect that there is methanol contamination ethanol, you can also take the, if you have the GCMS in lab, you can take this what do you call this sample in the lab and analyze for ethanol and methanol. You get ethanol and methanol not are the same GC what do you call a graph or chromatograph. Yeah, but in terms of Raman, you can actually use to differentiate between if you have a methanol contamination, you can run the Raman spectrum of the methanol of the methanol, and then use this as a basis to detect contamination of methanol inside ethanol. So this is a what do you call a portable technique. But in other what do you call a technique, you can use GCMS. So try not to actually limit yourself into only one technique. Try other techniques. Like for example, if you have contamination, you started contamination, right, in a sample. So you can try that technique, run the spectrum of the analyte you want to detect. If you get other wave length, other wave numbers, then there is contamination. But try to substantiate that contamination by using other techniques, for example, GCMS. Try not to stick only on one technique. Yeah? So that is one of the solution. If you have other solution, you can actually think of, which I might not be familiarized. So is there any other question? I hope that answered the question.
Okay, thank you, Prof. Wan. Anyone to ask question directly? Okay, Mr. Khairuddin.
Yeah.
Please.
Thank you very much. Professor Wan, it sounds that this instrument is very powerful tool to identify chemical species, know sample preparation, visible using visible spectrum, portable, and then we cannot use it to determine the concentration quantitatively. So how this instrument works to determine concentration chemical species quantitatively? How this works? Thank you very much.
How this instrument can be used to
Measure the concentration quantitative.
Yeah, quantity detection. Yeah, quantity detection, right? Quantity meaning quantity detection, right? Right. I mean, quantitative. I mean, you want to determine the concentration of the analyte, right?
Yes, quantitative.
Okay. Yeah. Okay.
Concentration, I mean.
Yes. Okay. So in all sensors, all quantity sensors, you must have calibration. Like for example, if you have the pH meter and like that, there is a quantitative sensor for hydrogen ion. You know, you have pH meter, right? You use pH meter before. So pH meter electrode is a quantitative detection method for the presence of hydrogen ion, right? So when you have the meter pH, and then when you have the electrode, you must actually calibrate with different buffer solution, right? pH 4, pH 7, and pH 10, right? So you put the electrode inside the pH 4, you get the reading, you calibrate pH 4. And then you wash the electrode, put in pH 7. When you get the reading, calibrate to turn to pH 7. And then you take the electrode out, wash it, and then put in pH number 10. And then when you get the reading, you calibrate to number 10. And then you have the calibration. That calibration data is stored inside the meter pH, right? And then now, when you have an unknown pH value, pH solution. You want to know this, what is the pH of this solution. You put the electrode inside the solution. That meter will give you the potential reading. This potential reading has been calibrated, okay, because this potential reading corresponds to a certain pH value, but that data is already stored in the machine. So when you put the electrode inside the pH meter, in the solution, unknown pH, that electrode will measure the potential difference. The potential difference is converted into pH reading. That is how you do calibration. And then, so same thing, the same principle applies to any type of sensor where you want to do, when you want to determine quantitative detection. First of all, you must get the gold surface, and then you drop or establish what do you call a film onto gold surface with known concentration. Like for example, maybe you can drop like for example 1 ppm onto the gold surface and then evaporate, and then you run the spectrum, and then you get the peak. Okay, and then you calculate the peak height, and then you get 10 ppm, 10 parts per million, drop on the gold surface, evaporate, run the spectrum, and then you get the peak, right? And then you get concentration 100 ppm, drop on the surface, evaporate, and then you run the sample, and then you get the peak. So now you have peak height for 10 ppm, 100 ppm, 1 ppm, and then 1000 parts per million. Then you get a calibration graph, right? So that calibration graph is stored inside the machine. Now, when you actually measure the unknown concentration of the analyte, that machine will measure the reading or what do you call the counts per minute reading. That intensity will be converted into ppm concentration, because that graph you already stored inside the machine. The graph of the what do you call the intensity versus the concentration. The concentration is 1 ppm, 10, 100, 1000. Whenever you got this graph inside the machine, and then when you measure the same analyte but different unknown parts per million, then what you get is the intensity. That intensity correspond to a certain ppm level. That ppm level, when as long this intensity is measured, it will give you the ppm level. That is how you do the calibration and also the detection. So any quantitative sensor, you must have calibration first, just like pH meter. pH meter, you do calibrate using pH 4, pH what do you call 7 and 10. So when you calibrate using pH 4, 7, and 10, that data is already in the meter pH, right? So the electrode has been calibrated. The electrode calibrated, the data is stored inside the what do you call a meter. So therefore, when you measure when you want to measure unknown pH solution, you put the electrode inside, and then that reading will be converted into the pH reading of that unknown solution. That is how you do the quantitative. Any quantitative sensor, whether it's electromagnetic radiation, based on electromagnetic radiation, or based on potential measurement, you must have calibration. Any quantitative sensor must have calibration. So I hope that answered the question.
Yes, thank you very much indeed, Professor.
Okay, is it clear, Mr. Khairuddin? Okay. We invite to other participant to ask a question. Maybe you can raise hand from your Zoom.
Okay. Thank you, Prof. Wan Basirun. I have questions related to search for detect the bacteria, because I am quite interesting to detect the bacteria. Maybe we can take the example such as the E. coli. So while Raman scattering can provide the sensitivity to detect the bacteria such as E. coli, the sensitivity can be affected by the factors such as the concentration of the bacteria. So what is the option to increase the limit of detection to detect the bacteria, professors?
Increase the lower limit of detection. Okay. The bacteria, even like for example, COVID sensing, the bacteria, it has like for example, the bacterial wall, right? And the most important thing, it has a DNA. The DNA of the bacteria, meaning the DNA bacteria is basically unique compared to DNA of virus or other types of bacterial strain, like for example, E. coli. Yeah? So this E. coli has DNA, right? But if you want to detect the DNA of the E. coli, you must have the Raman spectrum of the E. coli DNA first, because then you can actually use this as a basis of detection. But this detection will be qualitative. For example, when you have the Raman spectrum of the DNA E. coli in a water sample, okay, or in a thin film, then you get the spectrum, okay. But you want to increase the sensitivity because this Raman you only increase up to 10, 10 power 14. So it's very, very sensitive technique. But you want to increase the sensitivity more towards 10 power 14. You can actually do it in terms of nano structured gold, like just now in the slide just now I said was you were shown the nano structured gold, right? Where is gold nanoparticle or nanorods or nano surface, because this nano surface will increase the sensitivity compared to just smooth gold surface. That is why, like for example, when people want to actually determine very low sensitive measurement for bacteria or virus, because bacteria and virus, even in small concentration, they can be detected as long the surface is being the surface of the gold is being put as small as possible, like for example in nano size. That is why, like for example, people go into nanosensors using gold nanoparticle, very small gold nanoparticle. This gold nanoparticle only can accommodate only a certain number of bacteria or virus bonded through the cell wall. So the cell wall must be bonded to the gold nanoparticle. So the smaller the gold nanoparticle, the fewer the bacteria or the virus can be bonded onto the surface. So that's how you get the enhancement. So compared to just bulk gold, because this what you call instrument, they have the special electrode. That electrode is basically smooth gold surface, or basically it's a deposited gold surface onto a thing. So this gold surface are basically all pure gold. So in order to increase the sensitivity, you can actually make the gold surface to become nano size. But to prepare it, you must prepare your own cell, because this what you call company, they market the Raman portable Raman, battery operated, and also the gold electrode, where you can actually detect the what you call the analyte by just simple absorption. But if you want to increase the sensitivity, go to very low detection. Like for example, now people have reported attomolar. No? Attomolar is basically billion in a billion. Attomolar or maybe femtomolar. It is even more sensitive. So by using nano-sized particle, gold nanoparticle suspended in solvent, and when this gold nanoparticle, because gold nanoparticle is a very small surface area, right, compared to just bulk gold. So when you have gold nanoparticle, people can go even below attomolar or even the level of femtomolar or attomolar. Attomolar is a billion in a billion, right? Femtomolar is million in a billion. Attomolar is even more small. I mean, smaller is a billion in a billion. So by using nanostructured surface, like for example, gold nanoparticle or gold, silver, caution nanoparticle or silver nanoparticle, it can actually go in the level of attomolar detection compared to just bulk gold surface. So that is, I mean, you've seen the slide before, and about gold nanoparticle. So that is one strategy of increasing the sensitivity of the detection method. Hope that answer the question. Yeah.
Okay, is it clear?
Okay, thank you, Professor.
Okay, maybe there is a question from Miss Fina. Miss Fina asked a question. Could you please elaborate further on example of Raman application in the biomedical field for observing structural and morphological change in bio? Can you
Okay.
yeah, example?
Okay. So in biological sample, basically you have in biomedical sample, like for example, plasma or skin tissue, you have lots of water inside. Okay. So water is the main constituent of biological sample, like for example, organ tissues, internal organ, and also fats, also proteins. So when we have structural or morphological changes in the biological sample, meaning some of the water molecule has been evaporated or maybe degraded, or like for example, blood tissue. Okay, blood is consists of blood is hemoglobin, right? In all of the biological tissue, you might have some blood sample. So like for example, blood. So blood is basically you have hemoglobin, and the middle is ferrum, iron 3, bonded with all the groups. So, like for example, when you expose this blood into a environment, it get oxidized, right? Like for example, if you notice blood, when you actually expose to the environment, it structural and chemical change will occur, right? So as long that structural or morphological changes is due to chemical changes, like for example, when you get the blood, fresh blood, you still get the hemoglobin, right? The ferrum bond with the porphyrin. But when you expose this blood into environment, maybe for a few days or few weeks, it becomes brown in color, right? Because brown color, because that ferrum is oxidized to ferrum oxide, ferrum 3 oxide, right? And what is the color? Ferrum 3 oxide is just rust, is brown color rust, right? That is why, like for example, when you get the fresh blood, it becomes red in color. It's red in color, right? Because that ferrum is not yet oxidized, But when you expose this blood into fresh blood into the environment, few days or few weeks, it become brown in color. Like for example, you have blood stains, right? Blood stain, fresh blood, you have just the iron with the porphyrin molecule, not yet oxidized. But when you have a blood stain, you're exposed to the environment for a few days, that blood stain become brown in color. Why become brown in color? Because that ferrum is oxidized to ferrum oxide, ferrum 3 oxide. And the color of ferrum 3 oxide is the color of rust. Rust in the metal. When you get rust, it's a brown color, right? So you have chemical changes. Okay. As long the structural or morphological change in the biological sample is due to chemical changes, like for example, the ferrum in the blood getting oxidized to ferrum oxide, then you can observe this in the the SCRS spectrum, because the ferrum of the fresh blood is not the same as the oxidized ferrum in the blood. When you oxidize ferrum by exposing this blood into environment, just a simple thing, like for example, you have a cow blood. A fresh cow blood is red in color, but when you stain the cow blood onto a substrate, like for example, cotton or a cloth, it becomes brown color after days and after days and weeks of exposure, it becomes brown color, because this brown color is due to the ferrum getting oxidized into ferrum oxide, ferrum 3 oxide, and the color of ferrum 3 oxide is brown color. It's just the color of rust. Okay, so whenever you have chemical changes from the bio, from the in the bio, if the bio sample if the biological sample induces structural or morphological changes due to chemical changes, then you can actually analyze, use this technique to analyze. But like for example, if the chemical state is still intact, then most probably you cannot observe anything, because this technique, just like other spectroscopic technique, the changes is due to the change in the chemistry, in the bonding or in the function group. Like for example, when you have ferrum, right, bonded with porphyrin, you won't get the same spectrum like the ferrum bonded with the oxygen. After oxidized, you get ferrum oxide. That ferrum oxide sample is not the same as the ferrum bonded with the porphyrin in the blood of the hemoglobin. So that is one. As long as you have chemical changes, chemical changes due to oxidation or reduction. But most of it, when you expose the sample in air, you get oxidation, right? That oxidation can actually induce changes in the ferrum of the porphyrin to become ferrum oxide. Okay, so whenever you have this, therefore, you can actually use this technique or any other spectroscopic technique to detect changes in the morphology or the structural, if this morphology or structure changes is due to the chemical changes, right? So like for example, blood, it can get oxidized, right? Blood very red in color because it is not oxidized. Sorry, I have to answer the phone. Okay. Hello? Yeah. Hello? Yes, yes. I will see you around, you come at 1 o'clock or 2 o'clock? Because I have a meeting now. Yeah, I'll see you around 1 o'clock, 1 o'clock. Yeah. Okay, thank you. Okay, sorry. So whenever you have chemical changes, when these chemical changes induce changes in morphology or structural, then you can use this technique to analyze the changes. Hope that answers the question.
Okay, thank you, Prof. Wan. Maybe this is last question from me. Prof. Wan,
Yeah.
as we know, the sample in SERS must be in nanoparticle size.
Yeah.
And we know nanoparticle tend to aggregate, which can reduce the enhancement effect and lead to non-uniform signal distribution.
Yeah.
On your opinion, how we can solve the problem, Prof?
Aggregation leads to non-uniform distribution. Yeah.
Yes, nanoparticle tend to aggregate.
Yes, yes, yeah. Okay. So that nanoparticle, like for example, when you have gold nanoparticle or silver nanoparticle, must be suspended in a proper solvent, So that solvent is colloidal solvent. Okay. Like for example, when you suspend it in a certain solvent, it might aggregate, right? But you must find a suitable solvent where you have a colloidal suspension, meaning colloid. Colloid is basically suspension of nanoparticle, and that nanoparticle is separated from joining together by this solvent. You can use, for example, a surfactant, a certain amount of surfactant. That surfactant can separate the nanoparticle from aggregation. Okay, because surfactant is basically to disperse, right? Surfactant, you have, like for example, long chain surfactant. It disperses the nanoparticle from joining up together. So that when you prepare a colloidal solution of gold nanoparticles or silver nanoparticle inside the solution, you must add a certain amount of surfactant. That surfactant will separate the nanoparticle from being aggregated. So that is the what you call strategy. So you can actually check, for example, you can actually check without the surfactant and with surfactant, because the function of surfactant is basically to separate and to disperse this nanoparticle from joining up together. So that you can actually that's one strategy. But that is all. But the amount of surfactant basically you have to do is just a small amount now. Maybe depends on the bond on the molecule structure of the surfactant, whether it's a long chain or short chain surfactant, or whether it's anionic surfactant or cation surfactant, because surfactant you have different types, right? You have anion surfactant, you have cation surfactant, right? And some of these surfactant, it works in different principles. So you have to be sure which type of surfactant you use. But the function of surfactant is basically to separate, to disperse, right? To disperse the nanoparticle so that it remains as a colloidal suspension. So if you study about this dispersion, nanoparticle dispersion in solvent, they always use surfactant. In some cases, the solvent is the surfactant itself. The solvent is a surfactant itself. In most cases, like for example, but if the solvent is not a surfactant, meaning you need to add a surfactant inside. So for example, water is not a very good solvent for gold nanoparticle because you get aggregation, right? So you need to put some surfactant so that surfactant can separate the gold nanoparticle from joining up together. So, but in most cases, the solvent function as surfactant. Okay, so that is the one study. If you cannot find a super solvent, if you have a limited choice of solvent, you can add surfactant to disperse the nanoparticle from aggregation. That is one strategy which people use. So that's it. How I answer the question?
Okay, thank you, Prof. Wan. Nice explanation. Maybe we about to end of session of webinar.
Okay.
So for closing, I want to thanks to all participants for taking the time to join us today in the webinar with topic SERS in biosensing. Hopefully, this webinar can provide a great source of useful information and knowledge for all of us, and especially for our keynote speaker, Professor Dr. Wan Jefrey Basirun, for sharing this valuable knowledge and expertise with us. Thank you, Prof, for your presentation. We will also like to special thanks to Directorate of Internationalization and Global Partnership, Universitas Sumatera Utara, for facilitating this morning's webinar through the equity program. If you have any additional question or would like to continue the discussion, feel free to contact us maybe by phone or by email. I am Agung Pratama as the moderator of today. Apologize if there are words and action that are not in place. Once again, thank you for your participation. Have a great day, and we look forward to seeing you at our next event. Assalamualaikum warahmatullahi
Thank you very much.
wabarakatuh. Thank you very much,
Yeah.
Prof.
Thank you.
Mas Irul. Thank you.
Okay, maybe I end the session.